Hello, everybody. This is Coach Meinbauer for AP PreCalculus. This is 2.15 semi-log plots. So brand new thing here for PreCalculus is these semi-log plots. They look like this right here on the right-hand side. If you notice, the scaling is a little bit different than what we're used to. What it does is it takes our outputs, our y values, and scales them logarithmically. Which means that instead of increasing by 1 every time or by 10 every time or by a constant number, it's actually multiplying by a constant number instead. So this plot right here is multiplying by 10, as you can see. So we don't have a 0, but we do have a 0.1, and then times 10 is 1, times 10 is 10, times 10 is 100, times 10 is 1,000, times 10 is 10,000 or 10 to the fourth. Okay, so all we're going to do is kind of learn a little bit more about the semi-log plot and go a little bit deeper into this. We have done one of our stuff. One of our lessons covered a little bit of this. We're going to cover this a lot more now. That being said, let's do our first example here. We are given the exponential function f(x) equals 2 times 7 to the x. Complete the table of values, and then we're going to go ahead and plot these. Okay, a couple little hints here just so you know what 7 to the third is, and so on and so forth. All right, so this is 2 times 7 to the 0, so this is going to give me a 2. If I do 2 times 7 to the 1, that's going to give me a 14, because don't forget that 2 times 7 squared is 49 times 2 is 98. It tells me what 7 to the third is, so just times 2 is going to be 686, and then the next one's going to give me times 2 for the 7 to the fourth is 4802. Just checking my cheat sheet, make sure I didn't do anything wrong. Okay, so now what we're going to do is we're going to do our best that we can to plot these. So at 0, we're at 2, so it's actually going to be right here. That's 1, next line is 2. At 1, we're going to go to 14, so here's 10. The next line is 20, so it's in between, a little bit lower than half. At 2, we're at 98, so that's almost 100, so I'm going to go just below it. Kind of really hard to tell in that little space right there, but I'm supposed to be in between the 90 and the 100, closer to 100. At 3, we are at 3 is right down there. We're at 686, almost 700. So 1, 2, 3. Sorry, this is 100, 200, 300, 400, 500, 600, 700 ish. Right there, just under 700. And then for at 4, we are at, and we're in the thousands. We're almost at 5,000. So 1,000, 2,000, 3,000, 4,000, almost 5,000. Just notice me counting on this video is kind of stupid because you can't see my little ticker right here. So just pretend that my ticker was next to the thing as I was counting each one. All right, so if I were to connect these lines, these appear to be what? These lines appear to be linear. So if we connect the lines, maybe just one E in the word we. If we connect the lines, or connect the points, the plot appears linear. Okay? So if you want to know what the slope of that line is, like if we were to plot all those points, we can actually find that by linearizing this exponential data. So what that means is we're going to take the data that we have here and we can rewrite it out as this function right here. Oh no, I lost electricity. Don't you wish it was just that easy to pay your electrical bill is just to move your hands? Okay, anyway, so a couple of things here for this. I got thrown off by the lights. Okay, so I'm able to convert a b to the x into this linear y equals whatever just by taking the log of just the outputs only, nothing else, and I'll convert the inputs. So n is going to be like the what's being multiplied by every time. So on the last one we had a base 10. So n represents our base. I kind of wish b represented base, but whatever, because we're using the exponential part. B is of the OG base, the exponential base, and then that's the so that log sub n of b represents our slope. And then our y-intercept is that log sub n of a. So the a represents the initial value, n represents the how much we're increasing by the log, the base of the log, and then b represents the base of the exponential. So if we go to our previous problem here, we have n is equal to 10 because we had our scales were increasing by 10 every time. And then I can plug everything else in. So we have y equals log, I don't need to write down the 10 because it's the base 10 of 7, all right, times x. So my slope is log 7 plus log 2. So log 7 represents the slope, log 2 represents the y-intercept. Use the following table of values to graph the points on the semi-log plot. And then does the data indicate that the exponential model would be appropriate? So we're going to plot this. We're going to figure out if this is exponential. Again, if our semi-log plot appears to be linear, we are exponential. Let's see if this one appears to be linear. So at 0, we're at 0.1. I'm going to zoom out a little bit so I can get everything on the same screen. Okay. At 1, we're at 0.5. That's 0.5, by the way. At 2, we're at 90. So go to your 10s and count up. So that it's going to be just the line underneath the 100. 3, go to 400, which was in the hundreds. 400. And then at 4, go to the 700. So 100, 200, 300, 400. It's about there. If I were to connect these, do these make a line? No, it kind of looks a little logistic. You don't know what that means yet. It just means that it's a little bit curvy. Okay. So is this exponential model appropriate? No. So the exponential model is not appropriate. Because the plot is not linear. All right. And then number 3 here, number of bacteria growing in a culture is measured every 5 days. So our scaling here, you can tell is by 5s. For 30 days, resulting data is shown in the semi-log plot below. The function b gives the number of bacteria for t days. What is the function b of t? So I have these plots. This is exponential. So I need to go ahead and write this as an exponential function. So what I'm going to do right here is I'm just going to pick 2 points. I'm going to go from there, and we'll figure it out. So the 2 points I'm going to pick right here, I just see 10, 100. That looks like a pretty easy one to pick. I can tell that clearly is 10, 100. And then 15, 200 is the next one. Okay, a couple different ways to tackle this. You can always tackle this one by just using the generic equation y equals ab to the x. This one does specifically talk about doubling every 5 days, so I'm going to use that to my advantage. So since we double every 5 days, we've done this with the exponentials. That's going to give me the generic equation of b of t equals a, and then 2 is the r value, 2 to the t over 5. Okay, just to make sense of that, every time that t reaches a multiple of 5, this thing doubles. So every 5 days. If you plug in a 5 into this, you can tell that it doubles. If you plug a 10, that means it's going to double twice because it doubles 2 times in 10 days. Okay, so now with that, we have our, we can find our a value pretty simply by plugging in any of our points, actually. I didn't need the 10, 100 and the 15, 200. I just need one of them at this point. I would have used the 2 points to find the A and the B value. But since I already have the B value because it doubles every 5 days, I can go ahead and just find the A value. So I'm going to just plug in a 10 and 100. So B of t is 100. And that is going to be A times 2 to the 10 over 5. So this is 100. equals 4a, because 10 over 5 is 2, so 2 to the 2 is 4, 4a. Divide both sides by 4, and a is 25. Okay, so my function here is b of t equals 25 times 2 to the t over 5. Okay, so there you go. There's your notes there on semi-log plots. Do not forget to like. Do not forget to subscribe.